Meanwhile, I will just show you some steps of how to do this with any kind of software. You can do this. Like the first step is hardware. You have to initialize. You have to connect your hardware with the software. Then the second one is you have to go to hardware window, right click and go to acquire data. There you have multiple options. You have to go with the first option, which is line sample. There you have to align your sample. If you are using very big like sample, which has a very big size, you can align them easily. If you have very small size, like will take today, will take very small size samples, there you have to be very precise in alignment. So there you have to align. You have to put that plus sign in the center of the window. After the by using these xy knobs, you can xy movement, you can do that. And then the second step is you have to acquire your data. So again, you have to go to hardware, acquire data, and there are many options in which you have to choose spectroscopic scan. There, after clicking that, you will have multiple options in which you will choose spectroscopic scan, and after that you have to enter your angle, in which angle you want to scan your data, and after that you can go for your scan. After scanning, is completion of scanning, it will ask you to save the data. Once you save your data, you can enter your model, whichever you have some knowledge, what kind of substrate you have taken and what kind of material you have coated over it. So you can choose model according to that. Okay, and after add layer of substrate, there will be no option of fitting, and in the upper thin film, there will be an option of fitting, like thickness, N, K, whatever you want to know, you can go for it. And then you have to open your generate data window by going to window, and there will be one window, generate data, and then right click and go for generate data. It will generate the data for whatever model you have provided, and after that you have to go for fit window. There you have to go for normal fit. Generally we go for normal fit. You can go with other fits also. Okay, and after that you will see that all the parameters are there in your window, in fit window. And in the graph windows, you can see they all are fitted well, and whatever the graph you want to choose, you can go for it. Like if you want to choose psi, you can go choose psi by right clicking and go. You can go to type and psi, delta, n, k. There are so many parameters. Whatever you want to plot, you can plot, and you can plot two y-axis together. Okay, so these are the simple steps. The soft copy of these steps will be shared by after this workshop. So these are the steps we generally follow. I guess everybody is there. We can start. If anybody has any question till now, and for any related to any sample or anything, any software regarding these steps. Okay, we'll wait for one more minute. After 11:10, we'll start with our samples. So today we'll start with, yesterday we have explained that we cannot take our normal plain glass as it is because it is transparent. So after that we were explaining this regarding the scotch tape. So we'll start with today with the scotch tape itself. Okay. So as you can see in the camera, this is a plain glass and this is a scotch tape. So here many people will ask that we are not using any plain glass. Actually, none of us work in the thin film. So we right now we have not any such kind of sample which is very precise for thin films. We have simple glass, so we are using that. If you have borosilicate glass or any specific glass, that the roughness will be less in them. So we'll be showing this simple glass roughness also, how you can calculate the roughness of your simple glass. So with we'll start with scotch tape, and then the second one will be we just um, mark with the help of marker. We have just marked this as black color. That's it. We'll explain these two examples in case of simple glass. If you have some specific kind of glass, you can go for it. Right now, since due to lockdown in IFER and NCL, we don't have right now with us any specific glass. So I think it's already 11:11. So I will start with the examples. If anybody has any question, he or she can ask, or shall I start? Okay, so after initializing, the second step was we have to align our sample. So for that, we have to mount our sample. So today I am mounting the simple glass with the scotch tape. Okay, this is the back side of scotch tape. So I'm putting it in downwards. So, okay, we have, so the next step was align our sample. So we have to go in the hardware window. There you have to select acquire data, and in which you have to select align sample. So it will show you this. Because this is a transparent, it won't show so much area of gray. So it's not aligned yet. So by using these knobs, you can align that. So you have to, as we already discussed, we have to simultaneously check the alignment in our software, since it's absorbing. Okay, sometimes if you are taking glass substrate or any which is very transparent, so sometimes it happens that the gray rectangle will disappear. So you have to recheck that is your detector getting the signal or not by seeing that black hole in the detector. The white hole, white spot should be inside that black spot. So uh, okay. Okay. Uh, because of this glass, it's not stable because roughness is very high here. It's not optically smooth that much as compared to silica. So it will take some more time. Okay. 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 This is aligned now. Okay. After alignment, the next step was we have to generate our data, experimental data. I mean, so we have to switch on our graph window where we can simultaneously see. So go to hardware window. You have to go to acquire data. There are many options in which you have to go to spectroscopic scan. We'll go with spectroscopic scan. Here we are considering we have no idea regarding the angle, so we can go for the full angle. But here I have some idea, so I will go from 50 or to, for example, 70. So for resolution, I will choose 25, and the step size I am choosing here is 5. You can choose any step size. Okay, so we'll go with that, and it will show us the graph simultaneously. So this is acquiring the data at 50°, then 55°, then 60°, 65, and 70. Okay. So this is the normal glass. If you are using some specific kind of glass which has S rough very small, like roughness is it's kind of optically smooth more as compared to this, you will see um, the graph will be different in that case. Right now we have not that example because of the lockdown. So I will show you that example in some book because they are already well known. So we'll save this data and okay. Mm, okay, so this is the experimental data, like it's nearly a horizontal line. So here we'll choose the next step was after generating the data, we have to provide the model and we have to generate our data for model and then compare them. Okay, so the next step will be like we'll go to we'll go to window and we'll switch on the model window. After switching on the model window, we'll add layers. So in this case, depending on our substrate, we'll choose Cauchy model. So okay, we'll go for Cauchy. If you have some smooth glass or borosilicate glass, there are models named as BK models. You can choose them also. So since this is a simple glass here, we are using this model. Okay. So there will be no option of fitting. I will fit all other parameters in the equation. Okay. So if you want to fit, if you don't want to fit, you can go for that also. Okay. Then the another step, another layer is I want to know. Okay, you can go for it and just do the fitting. If I want to know the roughness also, we'll add one more layer, which is already well known, named as S rough. It will tell you about the roughness of the of your film. So we'll add sref and we'll fit the thickness also. Okay, after giving the model, the next step will be we have to generate our data according to the provided models. So we'll switch on the generate data window and then right click and generate data. It will show you the generated data in the graph window also. So the next step will be we have to fit our data. You have to switch on your fit window also. Whatever, whichever window you want to fit and whatever the steps you want to follow, what you have to just go to window this and you can switch on any window you want. So we'll go with fit window and there you can right click and there will be many options. So here I'm going for normal fit. So MSC is reached 1.17 and it is matching with. So these are the values according to your Cauchy, sorry, and this is well known in the books, as you can see in this video. Another video. Okay, this is well known for rough plain glass substrates. As you can see, this is straight line. Okay, so I think it is visible. It's for plain glass. Okay, so if you have some smooth glass like borosilicate, thick glasses will be there. So your okay, so I will go with delta also. How will delta look like? So for that you have to go to graph window, right click, and go in type and just go for delta. So again it will show straight line in this case, because this is a simple glass. If you have some different specific kind of glass like borosilicate or any example, the delta will be like this. There will be some hump or peak kind of things will be there instead of smooth horizontal line. Okay, so in case of this glass, we can see that the lines are straight. So what if I will add the black color in the instead of scotch tape? So we'll take another example. Okay, so for that we have to go to hardware window. We have to load new sample. So this is the
Excuse me,
yes.
just I have a question like the parameters which you have chosen AN, BN, and CN. What does they depict? Can you give us a brief idea? Hello?
Okay, yes, yes. Can you come again?
Uh, okay. Hmm. The parameters which you have given AN, BN, and CN.
I have not given them like this. Okay, in Cauchy model, there are parameters. This equation is dependent on A, B, and C constant along with the wavelength. They are that parameters. I am not giving them.
Okay. So
For model,
what do they represent?
uh, okay. Okay. So for every fitting, they okay. This formula shall okay from there. No, sir. This they are just okay. If you they are just asking what are the ABC values in Cauchy?
Yeah.
Equation.
So Cauchy model, I think Monica explained. I have another conference in parallel going on. So there is a tea break, virtual tea break, but I don't have tea here, so I came inside this. Okay. So what is the question exactly? Can you ask me again?
Sir, this AN, BN, and CN values, what do they represent in Cauchy model?
See, it is an empirical model, and they don't. Unfortunately, these empirical models have no physics behind that. That's why I hate these mathematical models. So they are just out of convenience, and basically they are just fitting. So the application of Cauchy model is basically once you have that model, you can do interpolation and you can draw some other values. For example, value of n at only few wavelengths, and those, like for example, 5 6 different wavelengths, n value, and those n and lambda parameters fit that Cauchy model. So it helps you in industry actually, that because it is fitting that wavelength window, so you can find uh, another n value or some other lambda which is falling into that region. So you can basically do the calibration. You don't need to do entire measurement. So basically, and there is no physics behind Cauchy model actually. There is no physics. Okay, whatever physics was, I already explained you yesterday, and the leftover physics I'll tell you this afternoon and tomorrow. But please, I mean, these are just empirical equations. Does it answer your question?
Yes, sir. Yes, sir.
And these parameters have no physical significance. They're just absolutely, you know, only meaningfulness is that basically industry application in calibration purposes. You can just find some interpolation. Okay. Yeah. Who is the student?
So Shifali.
Ah, Shifali, I can recognize your voice. Okay. Back to Monica. Huh?
Hello. So Shifali, it just in maths we generally use polynomials. So it just kind of constant values to fit our graph. That's it.
Okay,
So
okay.
okay.
Ma'am,
Yes.
just one doubt.
Yes.
So I just simultaneously Googled what these ABC are like and that. If I understand it correctly, if we know n at particular lambda, then we can get value of k from it. Is that how we use those empirical models? Because we don't know all the things simultaneously, right? Am I understanding things correctly, or there is a
Uh,
mistake?
uh, okay, can you elaborate your question? I'm not getting. So, what I understood from your question is you want to know that can we get the n and k, I mean refractive index from these values?
Yeah, I mean, for calculating those refractive indices from the wavelength, that's why these empirical models and their equations would be used. Correct.
Yes, yes, absolutely correct.
So if we can find out, if we know enough of those constants that we can fit the model for n, then we can get the lambda and then fit it for k. Is it such an exercise that we can do with this model fitting?
Yes, yes. I will show you when we go to graph and when we plot n versus lambda, you can see the n since this is not smooth surface, optically smooth. Otherwise, if you have some good examples of glass, you will see the n versus lambda also.
Oh,
So,
okay.
okay, I will try to make it more clear to you. So generally, whenever we are using any mathematical formula or any, it just help us to fit whatever the data is there in the experimental data we generate. And it will try to fit with that model and give us some ABC constant. ABC constants are just A plus B by lambda plus C by lambda square, something I don't exactly remember the equation. It's just kind of this. They are just constants.
Okay.
So, depending on the lambda, like different lambda, they will just try to generate that points over there and try to fit our data.
Right. Okay.
Okay, from there you can get n also, but right now I have, since I have already told you, due to lockdown we have not that smooth glass substrate is there.
Yeah.
Otherwise, yeah, yeah, you are right. We can calculate n. Yes, as you can see in the window also, shared window, we can calculate n also.
Okay. Thanks.
Yeah. Any other question related to this? Okay. So, okay. So next step will be, we'll go with the same slide, same kind of slide. We have just put a black background by using simple marker. We had just make this in this small area black background. So is it visible? I think from here. So we'll try this sample. Okay. So for next sample, as we discussed yesterday, we have to go to hardware window and we can just go to setup and load our new sample. So I think it's visible that we have to go to hardware window, go to setup, and we can go for load sample. This will ask us to remove our existing sample. So, okay, the stage is moving in Z direction. Okay, and after that, we can remove a sample, the existing sample, and we can go for the next sample. So, okay, mount new sample. So here I am mounting the new sample. So this time, since I have taken instead of full slide, I have taken only slide small size of that slide, not very small but small. Yeah, you can say 1.5 to by 2 centimeters. So I'm making sure that it should be in the center wherever my light is coming. It should be in that area only. So I have mounted my new sample. So you can just check. Okay, it's coming or not? Yes, it's coming. So we can go for this. If it's not coming at that particular area, so we can move in X and Y direction. Okay, so it's coming. So the next step will be we have to align our sample. So right now it's not aligned since gray area is not coming. So we will check that white is white spot coming inside the black spot or not. Dubai, can you show them from zoom view? So it's not coming. It's not coming. That's why we are not getting any gray rectangle, dark gray rectangle because of that only. If it's visible in that camera, okay. So because it's very small. So what happened? What's there is like black spot is there and white spot is coming here. It's not inside that or not even like coming on the edges of the black spot. That's why we are not getting any kind of dark gray area rectangle. So what we have to do, we have to just move that white spot so that it can go inside the black spot. So with the help of these small knobs, I will just move and try to align that white spot inside the black spot. Sorry, this is the drawback of online workshop. Otherwise, you can go by hands-on also because this is very important step. So now you can see the dark gray area has started coming in the window. So for small alignment, we have to just see whether our plus sign is at the center or not. So, okay, this is creating some issue. Okay. Ah, okay. Okay, it's inside. And now we have to make sure that plus is coming at the center. Uh, since it's not optically smooth, it will create some issue for us. But if you have an optically smooth um, substrate, you can go for it. The area is okay. Okay, if it is not aligned by this, what we will do, we can cancel this and we can go for Z alignment. So I will change the angle and I will take some uniform angle because it was at 65, it was at 70 or 75 degree. So now I will align them. Okay, so right now the angle is 65 degree. So, okay, gray area is dark gray area is coming. So we will try at this angle also. Okay, it's coming, it's coming, it's coming. Yes. So as you can see that whenever we are taking very large area because the band angle is very large, so there might be chances there will be problem in the alignment. So preferably angle is between the 45 degree to 65 degree, because the edges of this ellipsometry will be easy to detect the signal. So it's aligned now. Okay, it's taking some time because the signal is very small. So we'll give them sufficient time because it's not optically smooth. Again, I'm repeating, it's not optically smooth. That's why it will take some time. So, okay. Okay, meanwhile, I will show you what are the samples we are taking next. So, this will be the practical samples, like very small samples, 0.5 by 1 centimeter will be the sample. This will be our sample for tungsten. This is very small. So these are the practical samples. And PMMA, in PMMA also it's 0.5 to 0.5 centimeter area. So this is not, still it's not showing because signal is not sufficient to align that sample. Uh, hmm. Okay. Still it's taking time because they are not optically smooth. Uh, Okay, we'll wait for 1-2 minutes. If it will be not there, we'll cancel the this because they are not or not optically smooth. But generally, if you have optically smooth glass, you can go for it. Like you can just with the help of any kind of marker or anything, you can just make them. You can just make the black background, and you can go for it. Okay, so okay. Because of black background, it's showing the area. Yes. Anybody wants to ask something? Hello. I think someone is unmuted. Okay. Okay.
I just wondered that in case we need the sample to be optically smooth anyhow, and it just is not, then what do we do in that case?
So, okay, as sir has already explained that
Yeah.
in case of
Sorry, I was
ellipsometry, we
repeating.
always need optically smooth sample. Then only we can go for it. That is the requirement of this instrument.
Okay.
uh, since you can see by yourself that due to this sample is not optically smooth, because of that only we are getting these problems in the alignment and everything.
Yes.
Hmm. So what I will go, I will try with some different angle also, if we can go for it. Again, we'll align this sample. Um, if we can, because they are not optically smooth. If you have very fine glass, you can go for it. Okay, still, if I believe it will not give us good alignment because of the roughness. Okay.
Yeah, on the hardware align tab, there's one thing written gain is equal to 4. What does this gain mean?
Like the more gain will be, the more area will be, the more area it will cover. The gray, what we can say, rectangle you are saying is the representation how much area it is using for alignment. The more gain will be there, like it's kind of how much information is
How much area they are scanning for
yeah,
sample?
kind of that only. The more gain will be there, the more area it will use, from the sample.
Okay, okay.
Still it's not uh, giving us an option for cancel, because whenever the alignment is finished, it will allow us to cancel. So the other way, if your sample is not aligned, how to close this? We can just use, as you can see, for exit, you can use escape, and it will again try to align. But this time I will say no, I don't want to align the sample or more precisely. Okay, in it's aligned, like the information is going towards the detector, but not exactly aligned. So if you go for this type of if I will try to scan there, the information will be there, but not full information will be there because the sample is not fully aligned. So if you want me to go for experimental data, I can go for it. Otherwise, we'll go for next sample. If you just want to check what is the role of alignment. Okay, so okay, we'll go with this because alignment is not there. So go to hardware, we have to go to spectroscopic scan. Okay, we have to, we'll go with the same angle and everything because we are using same kind of glass. Since there is no sample here, will as such not get any information of alignment. If you have optically smooth sample, you can see the difference, drastic difference. If your sample is not aligned properly, you will get less information in that case. So this is already not optically smooth, so it won't, and there is no sample, so it will not give you any good information about alignment also. So why I'm saying alignment here we can use, because the detector is detecting the signal but not properly. So that's why we will get some information, but not full information. Okay. Try to- uh, okay, we can go with this, the same, and we'll generate our data, and then we can go for normal fit. Okay, here you can see the MSC value is high as compared to the last one because alignment was not proper here, and you can see the fitting is not proper because the alignment was not full. So that's why it is very important to align your sample properly. So okay, this is okay. Uh, Now we'll go for practical samples. So till now, anybody has any question regarding the glass substrate? I'm again repeating the same thing, that since due to this lockdown and everything, we have not smooth glass substrates. So that's why we have just taken the simple glass substrate we have in our lab. So they are not optically smooth. If you have optically smooth glass substrate, they will show very good peaks. Okay. Anybody has any question regarding this? Okay, I just want to know one thing among as we have seen from last 2 days, many of you guys working on thin films. So I just for next workshop or for further reference, I just want to know one thing. May I know what kind of glass substrate you guys are using so we can just note it down for next time onwards. We'll try to arrange them for yes. Can you hello? Uh, Hello, can you come again, please?
Ma'am, we use soda lime glass.
Soda lime glass. Okay. Thank you so much. Any other kind of
Soda lime glass, quartz, etc.
was?
Sapphire,
Okay.
soda lime glass.
Okay. So
and ITO?
ITO. Okay. Any other kind of
Also molybdenum coated glass.
molybdenum coated glass? Thank you so much.
Al-
Thank you so much.
Alumina substrate.
Alumina substrate glass.
Yeah, and
Alumina substrate glass.
and
Okay.
steel substrate also.
Steel substrate also. Okay, thank you so much. Thank you so much. Since we
And
are not working in thin film, so we
and
need your information.
we are using mica for the uh,
Mica also. Okay.
mica
Uh,
sheet. Mica sheet.
mica sheets. Okay.
Okay, we use zinc sheets and the normal glass Rivera glass slides
Normal glass lights and zinc sheets.
sheets.
Yes. Okay. Thank you so much for your information. We'll use in further workshops. Okay. Any other kind of
Ma'am, can we generate our own library for unknown materials?
yes, yes, yes. You can do that. Like, see, I just want to make it clear that models are not generated by the industry or by the instrument owner. They what models we are using here are generated by researchers. Itself, like whenever you are going for new any kind of new film and it is very fine, you just publish a paper and you will propose that model for the first time for your sample. After that, whenever anybody is using that kind of substrate, they will use your model, they will use your information as a model. To make any kind of model, you can just edit the existing model, and you can model model is what model is just containing the information regarding your film. So what you generally need is n. Whenever you are going to publish your results, you have to provide n dependent on wavelength. You will provide psi dependent on wavelength, and these are the only information model has. Are you getting my point? Hello.
Yes, I'm getting.
uh, if you use XRD, this will be more easy to understand, since whenever we are matching with the existing data using JCPDS has always a reference that this was published by this in this year, and they will show you neutron scattering and everything, and every information will be there. Similarly here also.
Okay.
Hello, ma'am.
Yes.
Ma'am, how do we decide that our glass substrate is optically smooth or not?
Okay, as I have demonstrated yesterday, see, not glass, anything you want to know optically smooth or not, what you have to do, just, okay, if you, for example, you have ellipsometry in your lab or not, you have a pointer in your lab. Subhay, can you just bring a pointer, please? Uh, for example, you want to go for some measurement in for ellipsometry in some other lab. Before that, you want to know whether your samples are optically smooth or not. There is very simple experiment which you can do. I will show you. Just you have pointers in your lab. Everyone has pointers in their lab, so I will show you how you can see. This is a glass. Oh, Bhavna di, this is a glass which I'm saying this is not very optically smooth. So this is a normal pointer. You can just do this and you will see the spot. Spot is visible. Is it visible in the camera? Okay.
Yes, yes.
Yes, it is visible.
Then the next step is, this is optically smooth. Normal standard silicon dioxide over silica wafer. Just do the pointer where you will not see point. It will reflect. It shows that this is optically smooth. It will reflect the and from there you will get your information about your sample. This is the simplest experiment you can do to understand your. Yes.
And please repeat one more time how the laser
Yes.
is fitted on the sample.
Okay. This is a simple laser we generally use in our lab. Okay. So this is a glass substrate. So what you have to do, you have to just check. This is not optically smooth because its transmission is there. If you can see, the light is passing through the glass because it's visible in my hand also. Can you see it? Hello.
Yes, ma'am, it's visible.
Okay. So it's not optically smooth. Whenever you are taking any optically smooth surface, it will reflect the light.
Ma'am, is the red point is on the silicon or not? Is red point is spotting on silicon wafer is or not? Ma'am, it's not clearly visible in the image. I am just asking, if you are pointing the laser on the silicon wafer, is it making a spot on silicon wafer or not?
No. It's not making spot as spot or the. Okay, I will show you one more.
Spot. Only visible spot, just to see from the naked eye.
Yeah. It's because it's also. Okay, actually, due to camera, you cannot see. Okay, it's small visible.
Okay, ma'am. Fine.
Then you can say your substrate, your film is optically smooth. And if you have ellipsometry in your lab, you can go for more fine experiment. You can just check with your incoming light. You can just place your film over there. If it will reflect the light in the and you can see in the detector, it's optically smooth. Otherwise, it will show you very small. You will see more light over the your sample. I will show you because I have to load more again sample. Just give me 1 minute. I will again load new sample and I will show you. Tubhai, can you just zoom in it? Hello.
Okay, ma'am.
Okay. So I thought someone is asking anything. Okay. So this is a spot. Okay, I will show you. This is the simple white paper. You can see the spot because this is not optically smooth. Can you see the spot? Okay, because of this camera. ये वाला camera. Okay. Can you see this spot now? Or any kind of like this? Can you see the spot? It's not. Can you see the spot?
Yes,
we can see it.
Yes.
Yes.
Okay. Now I will place silica wafer, which is optically smooth. It's not visible from eyes also. It's not that it's not visible in camera. It's not visible in from naked eyes also.
Okay.
So in that case, you can say your sample is optically smooth. Is it clear to you?
Ma'am, it is the demonstration that it is the means the substrate is optically smooth or not. So if it is not smooth, so how can we
Yes. Come again. You are not audible, I guess.
actually
I Yes, yes.
actually I'm saying that you have demonstrated the substrate is optically means optically smooth or not.
Okay.
So how to make it if it is not there?
Okay. What's my see? If you want to do the like, if you want to characterize your sample with the help of ellipsometry, your sample has to be optically smooth. Okay. So, what kind of like method you are using depend on that. Your sample can be optically smooth or not. If I am making some solution and just mounting that on the glass light, it will not be optically smooth. So there are methods to prepare fine thin films which are optically smooth and which are very fine. So what kind of sample you want to like, if you are okay,
Actually,
for
sir,
example.
ma'am, actually, sir said yesterday that you need to blacken the backside of the substrate. Okay,
Yes, yes.
so
Hmm.
by that we can only means optically smooth our substrate. Huh?
No, 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 no. Okay, okay,
So
okay.
why we do that?
Okay, because glass, the simple glass is transparent, as I showed you, that it will not reflect our light from the sample. To reflect the light, because from that reflection only we'll get all the information. For that reason, will what we will do, we will just darken our backside so it will reflect all the light. Instead of transmission, it will reflect. Because of that only we'll do backside as black. It is not at all related with the roughness of film, because what we are doing, we are just one side we are doing black on the lower side, and then we our sample will be on the upper side. There is no relation that if I am darkening the lower side, it is related with the thin film roughness and anything. To make optically smooth film, you have to go for good methods, like there are physical methods.
So here we want to reflect the light. So that's why we are doing the blacken from backside.
Yes,
That is
yes,
the purpose.
absolutely. Yes, absolutely.
Okay, okay,
Because that reflected light will give us the information about our sample.
okay.
Hmm.
Can you show the demonstration means, for any unknown material, the model fit to generate the model fit?
For unknown material to generate the new model.
Yes.
Okay.
Any simple for means.
Okay, okay, okay. Okay. Let me tell you very in a simple way, that since none of us is working on thin films, we have no new sample with us because we are not working on thin films, and we planned for that also, but due to COVID in Pune, the ICER and NCL both are locked. Even we also came with the special permission, so it's not possible for us to make new sample and demonstrate with model. But yes, I will demonstrate you other than these samples, what are the common not common, what are the samples you can how you can do your own samples. But for model demonstration, if you want me to go for new sample, very new sample, which is not reported or which does not have model till now, sorry, because of this, we are not able to do that. But yes, you can do by making your own model, and for that you just need if you have, okay, I can help you in this way, that I will try to do, just explain how you can do that. What if you are very sure about your film, that they are very optically smooth, and you have checked by AFM also, and you have checked because AFM will give you very fine atomic layer. You are very sure that your film is very fine, very, like, very smooth. So just go for ellipsometry, do at different angle with whatever wavelength you have, go for it, and just you have your psi and delta plot with you, just and go for with the for n and k. And now you will ask me how I will go for n and k. So whenever you are using new material, your material will be lying somewhere with some other material. Like if you are going for, depending on like what kind of sample you are using, depend on that, the same kind of nearby same kind of materials will be already there in the literature. So with the help of that model, you can, yes, okay, with the help of that model which is already there in the literature, which is nearby your sample, you with the help of that you can create, you can modify that model according to your sample. So for example, like, um, I am not sure about that it's known or not. If, for example, iron oxide is well known, maybe someone has already made one model for iron oxide. The second will be iron sulfide. If you make any film of iron sulfide, so the best approach is use the model of iron oxide and modify that model according to your data, and whatever the information you will get, depend on your MSc values and everything, you will get the information that the graph you are getting will match with the existing model or not. It will modify the existing model, modify, and at the final, after many trial and error, obviously since you are doing for new sample, after many trial and error, you will get the information about your iron sulfide also. Am I clear to you, or if you want to ask anything? Hello?
Yes. Sometimes what happen, we try
Hmm.
to means fit the model for unknown. Okay,
Hmm.
and we already know the thickness of that material. There should not be that one. But after fitting, we get the means, we are not confirmed that this data is correct or not.
Yes, absolutely.
So
Whenever you are
how can we confirm? Means
okay, so okay, yes, I agree with you. Whenever we are doing for the first time, we are not that much sure about our sample. So I'm okay. I can just suggest you what you can do whenever you are making film. Just go for different spots, and the data should be within the error. And if you are getting same kind of data every time, then you are sure that whatever the data you are getting for your sample is absolutely correct for your sample only. And yes, obviously you cannot just prove with the help of ellipsometry only. You have to, for the first time, you have to prove with the other microscopic techniques also, that these are the optically smooth thickness and everything. And after that, I think if you are going with multiple trials and you propose that every time you got this, that will be, I guess, that will be perfect for your sample.
as we record the cross sectional view of that film with the SAM, and that
Okay.
thickness is not equal to this one. So which one will we consider?
See what it will not match, because what happened is, like, whenever we are getting the information, depend on our input, our output will always, our information output, I mean here is information, will always depend on our input. If I am using some other kind of energy, the information will be slightly or more different. There I'm using some other kind of energy, some other wavelength. Here I'm using some other wavelength. So the information will be different, for sure different. So for example, in ellipsometry itself, if you are using different wavelengths, like here we use some different range of wavelength. If you will try here and in other instrument which have some different wavelength, you will get different thickness, because the input is different, the wavelength is different. Depend on our input, the output is dependent on our wavelength also. Whatever the thickness we are getting, it depend on that also.
Ma'am, our film thickness is constant. Okay, and the techniques that we are using, it's giving a different thickness. So what is the use, why we use these techniques? Because it's not giving us the accurate data.
No, accurate data, what is okay, sorry, but there is no accurate data. Yeah, like, you cannot say accurate at all. Do you believe whatever the information you are getting in TM and anything, like for particle size, forget about the thickness, if you are talking about the particle size, they are accurate? No, I don't believe on that, because whatever the information you are getting is depend on your electron beam, like energy you are providing. So you cannot say accurate, yes. But if you are using some different like, okay, for example, you work on thin films or nanoparticles, may I know that?
Ma'am, both.
Okay, so because I'm working on particles, so I will explain on that point of
Yes,
view.
I'm also working on nanoparticles and thin
Particles,
films.
okay.
Both.
Okay, so I will explain you in that respective. Okay, whenever, okay. So for example, we are taking two different techniques to find out the particle size of our particles which we have made. So in TM, for example, I am getting from 5 to 10 nanometer size of my particles. So when I go for some different kind of technique, like there is one technique named as SAXS, which tell me about my
Zax.
ZEX, yes,
Yeah.
which tell me about my particle size.
You
It
you
will never, yes,
you do TEM.
huh. I'm
Okay.
just taking an example. I have done the 10 of my sample, TM, and after TM, I got the information that my particle size is in between 5 to 10 nanometer. When I will go for the different technique, the particle size will be different in that technique, because the input I'm giving is different in both the cases. Okay, how I can say more?
Hello, ma'am.
Yes,
So that's why we
Ma'am,
take the average size of that particle.
yes.
Because lots of sizes are there, so we calculate average size.
And whenever we are taking the sample and everything depend on that also, it will vary. Even in TM also, if you do multiple time TM, the information will be different. It won't match exactly.
hello, ma'am.
Yes.
So, ma'am, as you're saying that the information will be different for the same sample with different instrument. So, I want to ask, the ratio of the error will be the same for samples, or will it differ from sample to sample?
Depend on your instrument. Error will depend on your instrument also, no? This is what I want to say. Okay, I will ask sir to elaborate this more, because I think sir has already elaborated this in his lectures. If not, I will ask sir, because this is well known. If I am taking thin TM and ellipsometry thickness, the thickness will vary slightly more depend on your sample, and the way you are using the wavelength we are giving, that will be different. And there might be chances it will match in some cases,
So
but
which
you,
one will we report? for the
No, no, no,
paper.
no. You for if you are this is just my, I'm a student, and I'm not much experienced. So being very frank, this is my belief. We have to report both the things. I guess I'm not sure about this. This
But
question is
but when reviewer ask which thickness you consider here, so what will say? What will we say there?
so depend if okay okay. According to my point, it's not. I'm not sure that it's right or not. What my belief is, if I'm making model for ellipsometry, I will go with the thickness of ellipsometry because I'm making the model for ellipsometry. And I think we have to report. It's better to report using both the techniques.
So,
Uh,
ma'am,
uh,
can we take the average of TEM and ellipso
no,
thickness?
no, 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 no. They are both different instruments. Both sources are different. Both techniques are different. We cannot take average of it. Okay, for
Ma'am,
more.
Because we need to report only one data.
No, no,
ma'am,
no, no, no. Yes.
In this case, you can
ma'am,
report both the data and you can
Ha, yes.
compare the error margin that with these two instruments, the error margin is this much.
Yes.
And more
Some,
accurately, the thickness obtained with the ellipsometry is considered more accurate.
because this is more technically. Whenever you are going for thickness or refractive index, everything you are using with the ellipsometry. So it's better to go for if you want to make model.
ma'am,
Yes.
ma'am, as you were performing for the glass slab, you used Cauchy model.
Yes.
And you also said that there are one other model for a smoother surface. I don't remember the name.
BK. BK.
BK
Okay. I
model.
will.
Okay, okay, okay.
Shall. Okay. We have. Okay. Just give me
Okay,
a.
okay, okay, okay. Let me ask my question first. Let
Okay.
me complete my question. Okay, there are two models for unknown. I can say it in other way. Okay.
Hmm.
Can you do this? Can you do the measurement of thickness by using Cauchy for silicon dioxide? Does it matches?
Huh, yes, because Cauchy is what? Is it is a mathematical formula. It's not related to anything. It's a mathematical formula which depend on lambda only. And there are three parameters which are which we will generally say constants in mathematics. They are ABC. They will vary depending on your thickness and every information. Lambda is since lambda is varying in our case. So depending on your information thickness, whatever you are providing, it will vary the values of ABC. Yes, you can go for it.
Yeah, I have a question. Suppose if I'm depositing some material on on any substrate, which has an absorbing property. Suppose, for simplest, if I take ZNO, now you are shining a broad light with a broad range, suppose in 200 to 1000 nanometer. So ZNO has an absorbance in the range of 200 to approximately 380. So when you are doing the modeling, there you have for silicon substrate, you have put k is equal to 0. So what is going to be the case for ZNO deposited thin film? Do we have to put k is equal to 0 over there?
Okay. Okay. Yeah, okay. Initially, we'll assign k equals to 0, or even we. Okay. If you are not doing point by point, you are just doing normal fit. We are not even assigning k value. We are just fitting whatever the k value will of that sample will be taken in that model. Okay. I will. Okay, we will not assign k value as 0 if you are not doing point by point. In that case also, if you will assign k equals to 0, depending on your sample, it will fit and it will give you non-zero values of k
Okay, so you are saying we can start with 0, but it will give my actual value.
value. Yes, 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 it's just a start because theoretically k equals to 0. So for that reason we just provide reference that k should be 0, nearly 0.
Okay, and one more question. As you have said that we can blacken the substrate because it provides maximum, it will reflect the light. So
Yes.
what if, like in mirrors, if you do silver paint coat, because that will
Huh.
also act as reflector.
Yeah, yeah.
Yes.
So
Yeah.
blackening is not important. Like we can do
No, no,
anything
no, no,
that
no, no, no.
reflects light.
This is the simplest way because markers are available in all the labs. So we can just go for simple example. If you have silver or gold, whatever you have, you can go for it because we don't have in our lab. So we use simplest way, and it's the rule of research also. Go for simple way. That's the only point.
Okay. And just one more question, like how do you use ellipsometry in your lab? Like you prepare nanoparticles and then you coat it on a
Uh,
substrate and
sorry,
then
sorry. Actually, right now, none of us work on thin films. So we are not absolutely using any kind of method to make thin films. But you can use, like, what my point is, I am not sure I'm wrong or right, but what my point is, go for some sophisticated techniques because they will give you very fine optically smooth. If you just make nanoparticles and dropcast, it will not make optically smooth because whenever you will go for TM or SCM, you will see they are not smooth surface.
okay.
If
So
you have,
if we do surface modification like by APTS coating and then we deposit suppose any nanoparticle by electrostatic attraction method, so maybe that can work. I think so.
if your nanoparticles are very small, then if your nanoparticles are big, I think they will create some problem. If your nanoparticles are nearly 5 to 6 nanometer or less than that, you can go for it, I think. But it's depend on your sample, absolutely depending on the sample and whatever the method you are using to make it. It's
Okay.
absolutely depend on that.
And
But yes,
now, suppose for if for any semiconductor, we just can't prepare in powder form and just deposit. That method won't do. Just asking.
I believe it won't because again it depend on your particle size.
If the
Every
particle size is very
situation,
big, it won't do. I think so.
because it will not be optically smooth. It will not be smooth. Okay, you can do one thing if you have the samples and you have SCM in your because SCM is easily available technique as compared to ellipsometry and any other thing. You can just dropcast and go for SCM and see your surface is smooth or not. If your surface is smooth, you can do ellipsometry.
Okay. Thank you. Hmm.
Yeah.
Ma'am, can you demonstrate any means sample for how to record the reflectance of that using ellipsometry?
We are just doing reflectance. We are just doing reflectance mode only. Am I not getting your question? If you want to ask me something else,
Actually, I'm asking that.
yes. Hello,
Hello.
hello. Yes,
Am
yes. Please.
okay. I'm saying that we record the thickness here. Okay.
Okay. We are recording thickness also. We are recording N, K, everything. But yes, thickness also.
So we want to record reflectance of that film. So can we record with the help of this instrument?
Okay. Here we are recording everything in reflectance mode only.
No. As in UV visible, we take
Hmm.
the film. We record the absorbance, reflectance, transmittance.
Hmm,
So
hmm, hmm,
as
hmm.
it is there, I'm asking here for the reflectance also for the film.
Okay. The method we are using here right till now was in reflectance. If you want to go for transmittance mode, you can go for, okay, this sample is not, give me 1 second. You can choose transmission mode. We are using reflectance mode only.
Hello, hello,
Hello, yes, yes, yes.
ma'am. We are using reflectance mode for recording the thickness. Okay.
Yes.
So as we take the reflectance of that film, we want to record the reflectivity, I think. Huh?
Ma'am, he is
R,
asking,
Actually,
ma'am,
RP and
ma'am,
RS.
Ma'am, he is
Yes.
asking for reflectance spectra.
Yes, yes, yes.
R
That's
and
that's
P.
it. That's it.
Reflectance
Okay.
spectra. As you plotted N and K, please plot
Hmm.
the reflectance spectra. He's asking for it.
Okay. 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 So,
Okay.
okay. Uh, Whatever the I mean, what we say, software we are using, we cannot direct using this software. We cannot directly plot RP versus RS or any kind of thing here using this, because this is a old model and old software, old keys are there. But yes, in new softwares and new version of software, similarly as N and K are coming, you can there is option of RP and RS. Just you need to go for graph, go to type, go to whatever RP RS versus wavelength you want, you can go for it. This is very old instrument and old software. Because of that, there are limitations. But if you have new software with you and new updated version of software, you can go for it. Similarly, as N and K are there, you will see RP and RS options also. Hello.
Yes. Okay. Okay, ma'am. Okay.
Or what's my point is the okay, there are options of, sorry, just let me okay. Just give me one sec. After that, I will explain. Mm, hmm. Okay. So as you can see, this is a graph. Whenever you right click, you will see type. Are many options. You see tensai also. Whenever you go for tensai is what? This is the ratio between RP and RS. This is just simple. So it's very simple to plot RS and RP. But this is RS by RP, RP by RS, I think. RP by.
Ma'am. In type, there is option of reflection also, reflectance also. Please select that one.
Yes. But you will not see any kind of graph because this
Okay.
is old software and old instrument. This is what I want to say. Here you will see different things, but you will not. In this case only, you will not get. If you have updated instrument and updated software, you will get. This is my point.
Okay.
Okay. Okay. So any other question?
So actually, I just have a question regarding the basics. I am just little confused. Can you clarify it? It will be very nice. Suppose, like at Brewster's angle, the RP section goes near approximately 0. So in that case, will the delta be 0?
No.
Approximately 0.
No. Okay, I will ask my senior to explain this. Monica, okay, unmute. Okay, because she has explained you yesterday also regarding the Brewster angle. Can you hear me now? Hello.
Hello.
Am I audible?
Yes.
Yeah, okay. So I think Shifali is asking, right?
Yeah.
Shifali. So the answer to your question would be, I mean, the tensai is going to 0 at the Brewster angle. That is okay because the RP is tending to 0. That is okay. But at the Brewster angle, your angle, delta angle will be changing from 180 to 0. But exactly at the Brewster angle, it will tends to be at 90 degree, not 0. After that, after the Brewster angle, it will again decrease and it will tend to be 0. But at Brewster angle, it will be nearly 90. But tensai would be 0. delta would be nearly 90 degree.
Delta is
Yeah, say.
yeah delta. That means you're telling the angle.
Phase
Delta
shift,
is a
yes, phase
phase
shift.
shift. Okay.
Phase
Okay.
shift, yes. Whatever the phase shift is there between S polarized light and P polarized light, although they are lying perpendicular to each other, but the way they start with respect to each other, that will tell us the phase shift, right? For example, one is starting from 0, one is starting from pi by 2. So that pi by 2 or that phase shift will be telling us the delta value. Okay, so
Mm-hmm.
delta value will be at the Brewster angle, it will be near to 90 degree. But you know what happens around the Brewster angle? There's a sudden change from 180 degree to 0 degree. The change in the delta value. But exactly at the Brewster angle, it will be 90 degree, the delta value. Okay.
Okay. Okay. Okay. Now, why there is a sudden shift from 180 to 0?
Because there will be sudden change. Why? Because the one of the component, the p polarized component, would be less. Because in the equation we can see that the Fresnel coefficient Rp would be there, Rs would be there. So when one of these components would be changing drastically, you know, coming to zero value, so ultimately those components psi and delta will change. So what happens to the fate of the psi? It will go to zero, and what happens to the fate of delta? Delta will go to 90 degree.
Okay. 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 Thank
Okay.
you. Mm-hmm.
Yeah. Okay. Any other question? Yeah.
Any other question? Okay, so we'll go for our next sample. So the sample size is very small. As I told you, this will be, the size is nearly zero point 0.5 to 1 centimeter, zero point 0.5 by 1 centimeter. So I will show you how to mount these small samples. Uh, the Hmm. This is the small size sample. So what we will do, we'll just place it at the center and switch on our vacuum. Okay, this is the center. So there will be, the alignment is little complex in these cases. So this is at the center. Okay. So, okay, I have started the alignment. You just need to go to, in the hardware window, you just need to go to acquire data and align there. Okay. So this is it. Now you have to check whether the white spot is there inside the detector or not. For that, okay, since this sample is very small as compared to the standard ones, because standard ones are very big, so we have to take the help of these knobs, which will move the sample, this sample holder drastically. So with help of this, I have placed this in such a way that we will see the gray area. So this is the gray area. Now we have to uh, go for this, the small changes. Okay, I have to again do it because I have not aligned it when we are during the discussion. Because of that, its alignment is changed. So okay, it's doing Z alignment right now. So as you can see, this Z axis is also moving. So it's not appropriate yet because samples size is very small. As I told you, in case of small sample, there will be an issue whenever you are using very small. The gray area is not there. So I have to check whether we are getting signals in the detector. We are not getting any kind of signal in the detector. For that reason, what I will do, I will just move. Okay. So with the help of small knobs, we'll try that to put our okay. So now gray area is coming. Now gray area is coming. So now with the help of these knobs, we'll try to align to put this plus red plus in the center with the small movement of these knobs. Okay. Okay. Since sample is very small, we have to take care that will not go drastically at different position. Uh, uh, for small samples, you have to be very precise during alignment. It will take more time. So you have to be very precise. It's aligned, so we can go for cancel. Okay, again, it will try to check whether all are visible or not. All are visible, so there is no need of doing alignment again. Okay, so I will just close existing models and generated data window. We'll again start with 0. Okay, the first step was we have to initialize our instrument, which was already initialized. The second step was we have to align our sample. We have done that. Now we have to generate our data. Okay, we'll go for graph window and we'll go in the hardware to see what is happening during the measurement. What the next step is, we have to go for hardware. In the hardware, acquire data, go for spectroscopic scan. It will ask to replace the existing data. Yes. And now we have to assign the sample. Like, okay, I will tell you about the sample first. This is a tungsten film over silicon substrate. So I will assign the angle according to the silicon dioxide and tungsten, all mixture of all pseudo Brewster angle, which we generally named as. So I will go for 55 to 70 or 75. Okay. The step size will be 5. You can take 1 to whatever you want. So I will go for 5. And okay, here you can see the transmission measurements also. If you want to go for transmission measurement, you can just click over it. Here we are just using standard. So that's why I'm going for standard measurements. So, and you can go for anisotropy and everything because we don't have samples right now with us, such kind of samples to elaborate that. So that's why we are using just standard measurements. So you can go for that and it will take data at different angle. So since we have taken these samples from, we have borrowed these samples from someone. So what my suggestion is, at least make 2 by 2 nano centimeter sample. So if you are going for different angle, it won't take that much. It will not be that much critical for instrument to align every time if you are making your own sample. Okay. Okay, this is tungsten sample and it we have not much idea about this sample. So as you can see, the graph is nearly this. Okay. Try, see, do. Okay. 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 Now, since we have taken the experimental data, we have to go for model. So I will delete the existing model. Okay, we'll delete existing layers and now we'll assign, or we can replace them also. will go for silicon initially. Okay, then we'll go for silicon oxide. Why? Since whenever we are going for any making any film, if we are taking silicon, there are always chances that silicon dioxide will be there. So we asked that person whom we have borrowed this. They said that there will be no silicon dioxide because they have taken all the precautions. Still, will get silicon dioxide, as you will see. Will okay. I will fit the thickness first. Okay. So there are two ways. Both first is you can just go for silicon dioxide, fit them, and then add the layer, third layer. Or you can simultaneously fit silicon dioxide or tungsten. Both ways are correct, but both ways will take extra time because you have to do one fitting and then second. And there you are fitting two films together, two layers are together. So both will take time. So we'll try with the first method. We will try with both the methods. So okay, the second will generate data. Okay, and third will be fit. We will go with normal fit. Okay, this is not matching because it will not be, because it's not only silicon oxide. So here we got, now I will not fit this. Okay. Since I have not made this film, so I'm not sure whether what will be the layer by layer. If you are making your own film, make sure you have all the knowledge that whenever you are okay, the best way I will suggest you is whenever you are going for your sample, always take same kind of like we have silicon wafer, very big silicon wafer, break that. You always break that for your sample. Always make sure you have the reference silicon wafer with you. So what is the best way is always do first the reference that will give you the thickness of silicon oxide. Also put that silicon oxide thickness here, like in this, just put and do not click on fit. This is the thickness of silicon oxide which you have calculated from your reference sample. This will help you in your sample, the original sample for which you want to find out thickness and everything, your coated thin film. So here I am just assuming it's 31, and I know it's not correct because whatever information I'm getting, it's after the tungsten. Since I have not made this, so I have right now we don't have a reference, but it's preferable go for your reference wafer. Always, it will be better for you. So again, what we will do, again we will add layer, and now I will use tungsten model, and we'll go for fit. Okay, we'll go for N and K also. Okay, so okay, somebody was asking if I am using some new material, how we can make model. So as I told you that there is always first time reference, you can refer to this reference material, and this is already published. From there only they have made models. So okay, go for it, fit, generate your data, and after generating data you can go for normal fit. It will not exactly match. Yes, of course, because whatever the thickness we have provided in the silicon dioxide, it's not correct. So what I will do, I will simultaneously try to fit them. Okay, still I'm not sure it will give you good information or not, because right now we don't have the reference material. That's why we are not getting proper information about this. Okay. It will take some extra time. So, any question related to this? Meanwhile, it's going for fitting. Okay, there is announcement regarding the your second half session. Sir will start the second half session after 4, at 4. Please note down the timing.
Okay, so will
Sir,
it be from 4 to 6 or something? Or
yes, 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 yes.
okay, thanks.
Okay, so okay, if anybody is working in polymer, like in polymer field, we have PMMA polymer also with us. We'll show you. And okay, it's already 12:40. So what I suggest is we'll do polymer tomorrow in the second half. So right now we will demonstrate the complete East software also. So because yesterday also we planned to do that, because of time we have not explained that. If it will not work, I will go for complete ease explanation. So this is the same method. Here it is creating problem because the thickness of silicon dioxide is not known. So what I will just go for tungsten. I will delete this layer. This is not proper way of doing it, this fitting, because this will give me the information about tungsten, fine, but there is always silicon dioxide layer. It will not give me the information of that silicon dioxide. So if you have your reference material, please always add that layer in between these two. Still it's not matching, it's because the layer is there. Okay, so what I will, if you want to,
Madam, I think you have chosen a wrong model for tungsten oxide over tungsten over the silicon. It is a absorbing film. Metal is always an absorbing film, so you should use a different model, not a thermal oxide model of SiO2.
sorry for your, I mean, thank you for your information, but it's right model because whatever the model we are using, we tried before this also. They are correct because they are already well known. Before me, my seniors has already worked in this field. We have just taken the model from their reference.
Ma'am, as much I know, for metal oxide, the fitting is for absorbing films, and it is used as a Cauchy model, not SiO2. But maybe you are right. I don't exactly. I have learned all through this from the manual itself. So I'm not very much confirmed. But what I know is it should be a different model than what you are using right now. I'm not sure.
Silicon dioxide. Instead of, what you are saying is, instead of silicon dioxide, I should use a Cauchy model.
Because your tungsten is a metal, and metal is always an absorbing film. For absorbing film, the model is Cauchy.
Sorry, but my point is, tungsten model is already well reported. So why should I go for Cauchy model if it's well reported? I mean, Cauchy model is not a model for anything. It's just a mathematical formula to match whatever information is there. It just give me ABC constants.
Ma'am, exactly, you are right that it's a well-known model, but the fact is the described model is not always convenient according to our grown film. The models which are in the library, the Cauchy is a generalized model which can be used for any absorbing film, not depending upon the material which is to be which is to be measured. That's why I'm saying that, but I'm not very much sure. I'm
Sorry. Yes. But sorry, what my point is, if instead of tungsten, I will use Cauchy model or whatever model, I mean Cauchy model you are saying me, then what's the point of you making any model for any metal? For gold, it is well-known model. For tungsten, it is well-known model. It's for silver, it's well-known model. So I think there will be no point of studying the metals and making the model for them if I can go for Cauchy model.
okay,
Ma'am,
ma'am.
at least use it once.
Okay, ma'am. Fine.
Try it for by using Cauchy model.
Yeah, there's one thing, like, is tungsten an inert metal? Because otherwise a small oxide layer will be there on the top. I think so. If I
Yes,
kept it in ambient temperature.
yes. Obviously, oxide layer will be there. Definitely, oxide layer will be there. So, no, what my point is, since I'm not working in this field, but this is a logical question. If I am going for Cauchy model in every metal layer, then there is no point of making any. Okay, maybe you are right, but then I have simple question: why I will go for any kind of model which is already known for metal? There is no point of making any model for particular metal for yeah, layer oxide layers will be there. We have to add every layer, like in silica, after silica we have to add silicon oxide. Similarly, after tungsten we have to add tungsten oxide. Absolutely, I agree with that, but I am not agreeing with you on this, that instead of tungsten model we should go for Cauchy model, because Cauchy model, and if then there is no point of making model for metals.
It's okay, ma'am. It's okay.
Okay, so we'll explain now. It's already 12:46, so we'll explain the other software which is complete is. So I will till now anybody has any question? Otherwise, we'll go for second step. We'll explain the other software. Okay, so we'll go for other software. Okay, I will just close them. Hmm. Okay. Shall I or you? Okay. So I think many of you guys are using Complete is in your laptops or in your desktops. So you must be familiar regarding the Complete is. But here we are not showing the initialize part, that the first part, which is what we are connecting our hardware with the software, because there we don't have key with us of Complete is. It's a old model, old instrument, and this configuration are not matching. We tried multiple times, but configurations are not matching. So we just we will going to elaborate only the analysis part over there. So the like the steps will be same. You have to just take experimental data as we have taken in this software. There also we can just generate our data. So I will ask my junior Tubai to explain the complete is software. Okay.
Hello. So this is the logo of the complete software. So this is the same software, just the interface is different, and it is not connected with the hardware system. So it's written as not initialized. Okay, so there are the options, and these are the different tabs: in situ, analysis, hardware, and the options. So in options, we can change the wavelength, thickness unit, optical constant, and different configuration of the hardware system. So in the hardware tab, we already know that we have to align sample, display signal, system check, same as well as W wave. So completeness is actually older version 3.50. So right now the 6.30 version is in the updated version, but this completeness version is 3.50 version. So we have some the recorded database. So we take one data from the database and try to fit using the model. So we take one 60 nanometer silicon oxide on silicon. So these are the psi and the delta. So similar type. We can cross the double axis and we get the only psi. So then we can get the in also. And for the model fitting, so we are choosing silicon with thermal oxide mode. So then we try to generate the data and the fit option. In the fit option, we are selecting that premium thickness, perform thickness pre-fit. So if we select this option, so the software try to adjust from the approximate fit thickness. If we know about the thickness about our sample, so we can import also in that part. We can import also that part. If we near about some idea, it will be easily fitted. It will be fitted earlier. But if you have no idea, we can just perform the thickness pre-fit on. So by doing this, we generate data and try to fit. So it's well fitted. And the MSE value is 0.687. And the angle of offset is, so its total thickness is 58.54 and this is the standard error, 0.006. So according to same, so we can change the different format, and in that next version, in that updated version, we can copy this graph also in the graph stage. So here where we can change the color of the graph, we can symbol it. So symbol. So this is the 3.50 version of the system. So there are some limited options. In the updated version, there are more options. We can change the graph color. We can in that system also. So we can some other data also. We can check another one. Appeal. And so in analysis, we have to again go for the open, and we can take one data from example, silicon oxide on silicon. So this is the psi and delta value, and again we can fit with silicon with thermal oxide mode. So in the fit option, we can take the perform thickness pre-fit. Then the software try to pre-fit the thickness according to their adjustment. And if we know the value, we can put it here. So the MSE value is also 0.943, so it is well fitted. And the same, we can change the different parameter according to the option. So these are the similar like WS. The interface is different. In the updated version, we can change the graph properties also. and there are some more other options present in the updated version. So in this version, we just can change this psi, delta, n, k, and we can sketch epsilon 1 also. So these are the almost similar with that WH bar. So anyone have any questions in this? Hello? Hello?
Hello.
So anyone has any questions?
Actually, I want to ask you that the data you are taking here, that is experimental, okay?
No, no, no. It is not from our instrument. Actually, it is reported in that software. It's some examples data. Actually, we don't use this software to taking the experiment to observe the experimental data. It's at the database from the competitive software actually.
Uh, so this software is basically used for fitting the data, yeah?
No, 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 not at all. Actually, our system is not configured to it right now with this software. That's why you are not taking the data using this software. You can, I show now there are the hardware options also. So it is not connected. So it is showing that the hardware is not initialized. There are the same option align sample, display signal, system check, and you can report acquire our data actually. So actually, our system is not connected with the system with this interface. That's why you are not observe data with this software.
No. What I'm asking that we record the data from the that instrument. Okay, we save that data experimentally the data recorded data. We save that data and we can open it here and fit the model.
Yeah.
Hello, Anand. You can use any of the software to acquire your data and then you can fit in any model. This is just for demonstration, as many people ask regarding that we have complete E's in their labs. So they just want to know how we can use complete E's. They both are same.
Ma'am, your voice is not audible to me. It's not clear to me. Please
Okay.
repeat
Yes,
repeat
yes,
again.
yes. So Anand, what my point is, we can use any, either we can use the first software or second software. They will both can take the data. They both can take the data. They can both used for analysis. We are just demonstrating that you can use similarly the second software. Complete is software also. There is no this is not like we have to take the data using first software and then we can do the analysis. We can take the data in both the software and do the analysis in both the software. Whichever is available in your lab, you can use that.
Okay.
Hi, Monica. Hello. Hi.
Yes, yes.
Yeah, you just measured the tungsten. Can you show me the tungsten fitting over here in complete is? Is it possible for you?
Okay, actually, okay, yeah, we can use okay, what you exactly want to know me, I just know.
Like you have just measured, you have a data of tungsten like, because everyone is asking. So I think tungsten data is with you currently. So if you can just fit it over here and you can show the what different optical parameters we are getting in this software. Is it possible?
Yeah, I will show you, but there it's not like that. We will get different parameters in this software and we will get different parameters in that software. They both are from the same company. It's just the updated software.
Yeah,
Still, I will show you.
that will be helpful. No issues there. I can understand fitting is very different in different environments. I just want to see like what different parameters we are getting through this. So that's it. No issues with that. You can.
No, no. Okay, I'm not getting you. What? Yeah, they both are same software. I will show you, what you want. I am sorry, I'm not getting.
You just show me the tungsten data that you have analyzed. I just want to see how you are approaching the fitting in this complete piece. That's it. Your experiment
Okay.
data is with you. I just want to see fitting. That's it.
Okay.
And
Okay.
if we are getting any optical data, like whatever, I just want to see fitting.
Okay. Hello. Mayank, actually, we cannot open the data here right now because in whatever format we have saved, whatever format we have saved, sorry, in whatever format we have saved. Hello, am I audible?
I think your voice is breaking, but you are audible, I think. Yeah.
Okay. So in whatever format we are saving, we cannot open right now in complete it because okay, I will show you why I can't. Whenever we are opening, we have to open in this .sc format, and we have saved in .bat.
Okay.
Okay, this is the data we have saved in .dat format. If okay, if I will get permission in the second half, because we don't have permission to come in the second half. If I will get, I will try to demonstrate. If you save in .sc file, we can open it.
Okay, no issues. Can you let me know that which model library you will be going to use for that fitting? That will be sufficient. For tungsten fitting, which model library you are going to use? Like, so that will be enough.
Okay. Okay. So I will just initialize it. I will show you in the first software. Is it fine for you? Hello. Hello.
Yeah. Hi. And
Uh, is it fine for you if I will I will show you in this software,
I think
or you just want?
you have
Okay,
already
you just
shown me
want
here.
incomplete is okay, or
Yeah.
you just
Exactly.
want?
Exactly.
Okay, so you can just assign any model. So go to model, and okay, I will. You can reset it and go for it. You can open. I have to check whether we have model here for tungsten. There we have. Uh, Okay, we have not added any model of tungsten in for this software. We have planned according to the workshop, so we have just added for this another software. But we can use the same like I will show
Okay,
you same model.
okay, you can show me here in ways, if possible, in ways itself.
Hmm. Yes, this model we are going to use. This one.
General aspect. Okay. This is general aspect. Okay. And this tungsten, this sample is completely a tungsten metal, or you have deposited over something like silicon or something. So what is it exactly?
So this
The
is
sample.
okay. This is silicon substrate, silicon wafer. Silicon dioxide will be there because of the it got oxide and everything. And over it we have not we someone has coated tungsten over it.
Okay.
May I know your question? What you want to understand and what you want to know?
Actually, I wanted to see the fitting in completeness. That's it. But since it was not possible in your case, so
So, okay, we are taking simple examples over there. As Dubai has showed you for silicon oxide, we can just take another example which is already there for. Okay, I will take any example of like this silicon oxide over silicon, and you can just open it. This is the okay. Now we can just go for model. It's I think it's already there. Silicon substrate interface and then silicon oxide is there. So I will just put 0 over here. Okay, and we can generate our data and go for fitting. It's fitted, and the like thickness is this. What you want? Shall we explain from the initial using completeness, or you just want to fit? Hello. Hello. Hello.
yeah. Hi, Monica. Actually, I lost my network. Can you repeat your question? I didn't.
My question is, this is what you want that for one example on complete is. I am not getting what you want to know, like what you want.
No, just I said you. I just wanted to see the tungsten fitting. That's it.
Okay, tungsten fitting in complete is.
Yes, exactly. So you said that you don't have that model, so it's okay. I'm okay with
No,
it.
no, there is no point of model. The first point is we whatever data we have taken, it's not in .sc file, so
Yeah.
it will not open in complete.
Okay. Okay. No issue. Okay. Fine.
Uh, but if you go for complete also, you will get same kind of thing because they both software will give you the same information.
Okay.
Any other question? Any other question?
No, ma'am. Not at present.
Okay. So in the end, I just want to tell you a few things that since there was so much questions regarding tungsten and one person I don't still asking about tungsten. So, since you guys are working in pencil, so that's why you are saying that we should use Hoshi and everything. So my point is, just since I'm not working in this field, I have a cross question. Maybe you will say, why should you guys will answer, and whatever. I will discuss this with sir also. If I should, since you have tell me, I should use Cauchy instead of tungsten, then why anybody has given any model for tungsten and for any metal? Maybe sometimes when there is no matching in the with our data and everything, then for starting point we can use Cauchy model. But there, this is just my point of view that there is no such rule that we should go for Cauchy model whenever we are using metals. And I will discuss this point with sir also, because if this is true, I think there will be no requirement of making any model for tungsten or for any metal. So this is just my point. I will discuss this with sir. Uh, this is all. And if anybody has any question, we can take that. Otherwise, we'll close the session. And the next session will be at 4.
Yes, ma'am. Noted. We'll be there at 4 o'clock then.
Okay. Thank you.